Hello, this is the first segment of the speech motor system. So mostly we'll speak about motor planning and programming. And then the next segment is going to include, we'll focus on motor activation and motor coordination. So in order to produce one word, it is going to require a lot of effort. It will require about 90 muscles, and it will require a lot of cognitive coordination among various parts of the brain. But we are speaking more now about the programming for speech before you actually make speech, about the planning that goes on while you are preparing to speak. So first you begin with a script, with an intention, and then you develop a script for what you are going to say. All of this happens on a subconscious level, and then finally you convey the command to the motor cortex, and the motor cortex connects that, and it's connected with the muscles through the cranial nerves. And then the muscles then are activated, and they translate the motor program into speech productions, into actual movements by the muscles. But in order to ensure that the movements are accurate and meet the requirements for the intention of the speaker, these movements have to be coordinated, and they have to be precisely synchronized. And this requires sensory feedback. So the sensory feedback comes from, say, hearing, vision, and it comes also from the muscles themselves. The muscles have proprioception. So they send information about how they are moving, how they are oriented in space. Are they up, are they down, sideways, and so on. So proprioceptive feedback goes from the local place where the movement is taking place at, by the muscles themselves. So here's a summary of the process. It is 3 phases. It begins with sensory planning and programming. Sensory means there's no movement, but there's a lot of activity happening in the brain where you take, you make an intention, you have an intention to speak, and then you develop a script of what you say. That is the programming and planning. And after that, you feed it into the motor system, which is the primary auditory cortex. And then while you are moving the muscles in action, and they are in action, then you get the sensory feedback to coordinate and to guide these muscles and make them, produce coordinated movements. And there are structures like the cerebellum that contributes a great deal. The frontal lobe also contributes a great deal to the refinement of the movement. You don't just want any movement. You want coordinated movement that matches the intentions of the speaker. So this is exactly what I'm explaining. Sensory processing at the beginning involves planning and programming, and then motor planning is part of that, or the sensory processing. I'm going to show you how this feeds into the motor planning, and then you go from motor planning to motor activation, where the muscles themselves start to get the signal and move. And from motor activation, you need sensory coordination and refinement of the movement, which is going to kind of guide the process of motor activation and motor planning while they are happening. You need to get that feedback. So here you are going to see this line here, that deep line, has many names. It's called the central fissure because it's like central in the lobe, in the center of the frontal of the hemisphere, and it's called the Rolandic fissure, or the fissure of Roland or Rolando, or it is also called the Rolandic the central sulcus. So these are all names for the same thing. The gyrus in front of it is called the precentral gyrus from an anatomic perspective. From a physiological or a function, you call it the primary motor cortex, and this has a map of the entire body where you can see this cortex it continues between the hemispheres. Like this, for example, is part of the primary motor cortex of the right side of the brain. So you could see here on the other side, there's an area just like this, and it controls the toes, the ankle, and then the leg, and then here as you go up in this area, the torso, and then the hand and the arm, and then you keep going to the face, and then the lips and teeth and stuff like that. So all of these things, I mean, this is a map of the body you should be familiar with at that level. It's called the homunculus. Homunculus means little man. So if they have a map where a person would be sitting down, dangling his feet down here and leaning back, and you will see how this is a map of the body. But it's a motor map for everything that you want to move voluntarily. And then this gyrus behind the central sulcus is called the post-central gyrus from an anatomic perspective. And the function of it is the somatosensory cortex, or the primary somatosensory cortex. Excuse me. So that's from a physiological perspective. The primary somatosensory cortex also is a homunculus. It also, they put a person there, and that person will be dangling his feet here and laying, back. And instead of giving the movements here, we get the sensation. For example, in this area, let's say we have the face. Let's say you come to the muscles of the lips. That makes you move them, and across on the other side, right across this area, controls the sensation that you get. That for example, there's pressure, there's pain, there's heat, hot, cold. So here you get the movement, and here you get the sensation from that. From that organ. And the area in gray here in front of the primary motor cortex, that gray area is called the premotor area. Again, the premotor area, or the premotor cortex. So cortex is any part of that cover of the hemispheres. So you can say cortex or area. The premotor. So this is a motor, and in front of it, is the premotor area. And on top of the premotor area, that red, pinkish area is called the supplementary motor area. In front here, the greenish is called the dorsolateral prefrontal association cortex. And this in front of the foot of the premotor area. So you have the motor area, premotor area in front of it, here, this area here, and the one next to it, they both make up Broca's area. Broca's area is only found in the left hemisphere of the brain, and the frontal lobe, inferior frontal lobe of the left side of the brain, or the left hemisphere, and it lies in front or anterior to the foot, or the lower segment of the premotor area. So this Broca's area is called area 44 and 45, or Brodmann areas 44 and 45. This is the area that has the syntax, and it has the lexicon, the dictionary, and it has the grammatical rules. It also is responsible for motor activation. It does not activate by itself. No, it has the programs to activate for speech. So it sends its information eventually to the premotor areas and to the motor areas, and from there that is going to go down to the cranial nerve. So you can think of this like a layout or a template for something that you would like to make with a 3D printer. So you get the template here, say here's what the thing looks like and how I want the machine to produce it. And then you send it to be reviewed and refined and edited and so on. Then you just, then eventually it will go to the motor area here. The motor area is gonna just push the button and the thing is going to print on the other side. Or in our case here, the organs are going to speak. The area in front is called the prefrontal cortex. This is the area behind the forehead, and it is responsible for many things, especially executive functions, your decision making, your judgment, your ability to control what is going on in the body, and voluntary movement, mood, and it also contributes to refining of motor commands. But in this area, this is where you develop the intention to speak. So, in terms of the intention to speak, once you have the intention, it is not enough. You have to kind of develop a script. Well, I feel like I want to say something. Now, how do I say it? And how do I explain it? And then you get many mechanisms here to plan the script, to develop it, to generate it, and then to execute it after it is edited, to send it to finally the motor cortex. So we're going to go over the process. I just wanted to orient you to these areas. I wanted to identify a couple more. So the prefrontal association cortex and association cortex is an area that connects multiple regions, multiple lobes in the brains. It's like a highway, like a huge area that integrates various kinds of information together from different parts of the brain. So you have one here, you have the posterior parietal association cortex that's also integrates vision with sensory, with hearing together. And then you have here, it is not pointed out, the visual association cortex, and you have the auditory association cortex in the middle of the temporal lobe. So these association cortices, for example, match your ideas with your words, with your sounds, with different things that, different sources of information are integrated together with your memory processes and so on, so you can finally execute a motor command. The cerebellum here plays a huge role in coordination of movements and in motor learning, and we'll speak about it at some point when we speak about the coordination component. So I wanted to point out some areas on the superior parts of the sensory cortex here. These areas contribute to sensory feedback. As you move, the sensory feedback is going to be sent to the prefrontal cortex, to the motor areas, and to the premotor areas, so that your movements will be focused and on target. There are two other areas here. You see the corpus callosum, and right above it, there's a gyrus that continues from the back, continues going anteriorly. That is called the cingulate gyrus. it is, you see it when you open the two hemispheres, then you see that continuing from one side way to the, from back to front, and it is called the cingulate gyrus. It's by itself, one single piece together. The medial parts here, right beneath the motor core, the supplementary motor area, they are essential in rehearsing and in editing motor commands for speech before you speak. So then, the anterior areas of the cingulate gyrus are active in editing and refining. So these are association cortices, and as I mentioned, they are superhighways in the brain that connect one lobe with other lobes to get different kinds of information. Sensory processing for movement. By sensory, we mean that you use your senses in order to assemble pictures in your mind of what you want to do. So you kind of develop an image of it based on your knowledge and based on the environment, and then you say, this is what I want. It's like designing a building by making a miniature cardboard building and say, this is what I want the real building to look like. So sensory is because we do not move. It is before you make any movements. Not sure if this is a link, but let's talk about this and then the planning, and then later we are going to speak about later we are going to speak about the other areas. So just go here. So sensory planning, it begins with the sensory input from the posterior parietal cortex. The posterior parietal cortex, this is an area where you have sensations, maps of space, and sensations from your body, processing. And also, this area enables you to orient yourself in space and to know where your body is in relationship to the space you have. I hope this is not spoiling the image. It seems like there's something here going on. We do that. Okay, sorry. So you start with the sensory input from the posterior parietal cortex that generates internal representations in the brain about the external environment, like location, where are you, and where, what do you have near you, and so on. The internal environment, how are your muscles? Do they have enough energy? Are they, they have integrity, and so on. The geometry of the movement and the energy that results from the movement. Your body, your brain wants to calculate this energy before you actually do the movement. It's like you want to go to the store and buy, or go out to the movies. And then, oh, do I have money? You need to check and make sure that you have enough money before you go. You want to buy something. Oh, could I afford that? So the body wants to conserve energy, and it's going to measure and calculate the cost first before it engages in the actual movement, because the actual movement is consumption of energy. So these representations become the basis for the purpose of the movement. And then the major area that is responsible for this part is the prefrontal cortex. The prefrontal cortex relies on the images and the representations it receives from the parietal cortex. So there are big connections between the prefrontal area and the parietal cortex. The prefrontal cortex uses the information from the posterior parietal cortex to determine the purpose of the movement. And the prefrontal cortex is the central executive of the body. It is responsible for judgment, for making calculations, for attention, for working memory, for reasoning, for initiation. When do I start? When do I stop? So, and many, many other important functions that enable you to make goals and to pursue these goals and so on. So, the prefrontal cortex has 3 direct pathways to the basal ganglia. The basal ganglia are subnuclei that are buried deep in the white matter of the each hemisphere. And one of these pathways is dedicated to motor feedback or motor control. This pathway is a circuit that connects the thalamus with the prefrontal cortex. The thalamus is deep in the body, in the brain. And I'm not going to repeat much of this because it is presumed that you have anatomy before you come to this class. So through the input from the basal ganglia, the prefrontal cortex can control the strength of the movement. And I'll explain at some point how. So here you could see these are the basal ganglia here, and they are connected with the prefrontal cortex. And also, of course, they are connected with other parts. They connected with the motor cortices, cortex, and the sensory cortex. They are connected with the, frontal parts of the brain, and they're connecting with the occipital. So they are very important in motor, speech motor movements. So all we said now is that the prefrontal cortex gets information about movement and about the body in order to calculate the cost of that movement, in order to give you some representation, to make a model and say, here, this is what we have. So let's see what the planning looks like. So motor planning, the purpose of it, the outcome of it, is to generate what is called like a future map of the movement. That future map is called a sensory forward model. That it is like you say, I would like to make a building, in this area, and I would like to make it look like this. The sensory forward model enables you to construct, the script of, what you are going to say, and says, okay, here it is. So you can imagine the movement. Your brain can imagine the movement. That involves communication between the posterior parietal cortex and the premotor areas of the cerebral cortex. So, based on the input that is received, that the prefrontal cortex receives from the posterior parietal cortex, the premotor cortex is going to do this. The premotor cortex is going to specify the spatial features of the movement about the environment and the position of the body in space. So it's going to say to you, oh, your tongue is going to extend by this amount, by this far. And then your lips are going to do this. And and then it makes you gives you a detailed description of these movements before they happen. So now I'd like you to really, really understand the forward model. Think of it as a little model for a building or something. It is the play. If someone is going to make a play, they are going to design it and get the script and then, design it so that they can rehearse and do it. So the forward model constructs representations of the anticipated movement. It tells you what this movement is going to be like before you actually do it. It uses a copy of the motor command that is sent to construct simulations of the anticipated changes that occur as the result of the intended movement. Like, for example, it is going to say to you, you lift up your tongue here or put it there. It is going to tell you how is this going to change the frequency in the vocal tract. How will this change the flow of the air this way or that way? So it's going to give you, what is going to happen if you do that movement, and then you can stop yourself then before doing it if it doesn't fit within the program. And then so it provides also estimates of the cause and the effect of the relationship between the action and the consequences. So you'll be able to predict if you say move your tongue this way or your lips that way, this is the result. And based on that, you can plan ahead of time to make corrections before you actually do the movement. It estimates future sensory inputs based on the motor system outputs. So that means it has memories of, you have memories of previous movements that you made. And based on that, it's going to say, well, the average for these movements, you consumed this amount of energy or you did that. So here is the outcome. This is what you are going to do when you do that. The sensory forward model is going to, it involves the spatio-temporal constituents of complex movements. For example, spatio means it has to do with space. Temporal has to do with time. So it tells you kind of, if you do this, extend your tongue from here to there, it will take this amount of time, because it goes, space and time are a factor in movement and in speed. So these spatio-temporal components of a complex movement are stored in the form of movement schemas. A schema is like a first impression of something. Like you see something for the first time and say, oh, and then you your brain makes an image of it for the first time. Like a baby when they start to learn something. And then that becomes like a magnet where you learn more stuff about that thing, and then as you learn more, you keep developing more. So the schemas are the first impressions or first memories that you get, and they become the foundation on which you are going to build other skills. So you cannot build skills without having schemas. Then the brain evaluates movements in terms of effectiveness and accuracy. This is why both of them are critical. The movement with the lowest error rate and the lowest, usually, energy cost is preferred. It is the movement that you are going to execute. This shows you, more functions here about how to coordinate the movement, with planning and with the purpose and intention, and your language. These are, the pink areas, language areas. The premotor cortex. We said here the red is the motor, the pinkish in front of it is the premotor. So that premotor area is very involved in generating the sensory forward model. So the premotor cortex sends activating impulses to the primary motor cortex. So because, that premotor plans and then the motor executes. So it influences motor activity more directly by supplying about 15% of the pyramidal tract fibers that we will be talking about. So it has a memory bank of skilled motor movement activities in that prefrontal area here. So it enables you to kind of use this memory, the memories of the previous movements to produce one that is refined and accurate. So the role of the prefrontal cortex in this is that it receives commands, information. I'm sorry, that the premotor area, the premotor cortex or area, it receives command information from the prefrontal cortex. The prefrontal cortex is the boss. So it also receives sensory feedback from sensory areas, and that will help while the movement is ongoing. So the somatosensory cortex, the visual cortex, auditory cortex, and the cerebellum, all of them send feedback to the premotor cortex or area so that it can coordinate and produce refined movements. The sensory information is about balance, proprioception, direction of movement, coordination of the movement, and this feedback is necessary for precision and for timing of the movement. So, and for also making the required changes while you are making the movement. So sensory feedback is critical, and it comes from the somatosensory cortex, sensory areas, visual cortex, and auditory cortex, and the cerebellum. The cerebellum has to do with coordination, and it helps you get, that kind of contributes to the proprioception as well. And then the role of the supplementary motor area here is it contributes to the editing process. So the it is superior to the premotor cortex, as I showed before, and it is anterior in front of the primary motor cortex. It gives rise to nerve fibers that form part of the pyramidal tract that connects the primary motor cortex and the premotor areas with the cranial nerves. So that supplementary motor area also contributes some fibers together so that they make a pathway called the pyramidal pathway, or the pyramidal tract, or the pyramidal track. All of these are the same. So it communicates with the prefrontal cortex and with Broca's area, and the functions include planning complex motor behavior, contributing to editing of the motor script, and in coordination, it does so in coordination with the cingulate motor areas and other frontal lobe areas. So these are, again, planning complex motor behavior is one function, and the other one is to work with the cingulate motor areas and other frontal lobe areas in order to contribute to editing of the motor script. Now, so far, we have not spoken. We are just making the script. So these are the areas we were speaking about, and I explained. You could go back to the beginning instead of me speaking again, explaining them again. What is the role of Broca's area in the production of speech? Broca's area uses sensory representations of words from the temporal lobe. So the temporal lobe has memory, and it has sounds, and it has you can assemble whole words and stuff, comprehension. And it takes that temporal cortex, provides the information to Broca's area, and Broca's area then matches sensory representations, images of movements and stuff, with the articulation positions. So, okay, this is gonna say, well, this is the model that you have, and then it gets an image of the how the sound, the lips and the other organs of speech will move. So say, okay, this is what you want, and this is what the condition is of the articulators. If they match together well, then there will be activation. But Broca's area, it does not contribute to the production of individual words. When there's production of individual words, that area is inactive. So it is active before you articulate, and it is not active while you are articulating. So here, is Broca's area, as I explained, and it has motor speech programming, and the grammar, and the lexicon. This area, and actually it is not placed really very well here. It should be on the posterior part of the superior temporal gyrus. So the superior temporal gyrus is here, and in front, the posterior part of it is Wernicke's area. You can see now this shows you how tracks of fibers in the brain connect, one side of the brain to the other, as you could see here. See all of this commissure. They are called, commissures. And this is see how Broca's area is placed here, area number 22, and then Wernicke's, I mean. Broca's areas are areas 44 and 45, these two. And the commissure that connects Wernicke's with Broca's is called the Arcuate fasciculus. The Arcuate fasciculus, almost like the arched pathway. And so you have many, these commissures, of course, they connect what do you call them, association cortices together. They extend from one area to the other. So finally, the prefrontal cortex and the supplementary motor area and the premotor area and Broca's Broca's area and the motor areas, two motor areas of the cingulate gyrus, they edit a script of what you want to say, they rehearse it, and then they match it with the intention of the movement to make sure it is what you want, and then that integrated input, it will be transmitted to the primary motor cortex, the areas that are dedicated to articulation, speech articulation. We are going to stop here so that the video will be easier to manage, and then the second part is going to deal with motor activation and sensory coordination for speech. Thank you.